Well, welcome back, everyone. Nice brisk morning. So I want to, first I want to mention my nephew, John Mark, is visiting. John Mark Davis, same name as mine, considering coming to UF as a freshman in fall 2012, right? So, okay. Well, what I wanted to do first was to ask you all if you had questions about the project. This is the hardest project you've been faced yet. You're to use all of the techniques and algorithmic tricks and tools you've learned the whole semester for this one project. I've had some questions about it already, so I could repeat those outside of class. So I could repeat those questions and explain some details to you. Do you have specific questions though before? Okay, I dive in. All right. Well, let me explain what's going on here. The first step. So this is this QR factorization. So the first step is the symbolic work. This should take you all of about 10 minutes to get working. Okay, and if it doesn't, then you've done something wrong. All you do here is you use the existing QR and you just rip out the numerical work. Okay? And don't compute the householder vectors. You shouldn't need to compute the householder vectors. Just compute R. Now when you're done with that, you don't have the right R. You have R stored in compressed column form. But you don't want it in compressed column form, well, so transpose it. That's a one-line statement in MATLAB, and it's a one-line statement in your C code because you can just call the CS transpose function. Again, when you're working on this project, if you can use existing code from my C sparse code, then do so. If you want to use existing code from another student, then you fail the course. That's another story. So don't do that. But use my code. That's permitted. This is a solo project. It is not a group project. As I mentioned at the beginning of the semester, every project is a solo project. Okay, so you get the pattern of R, and now what you have to do is, and what I recommend, well, do this thing as a separate step. Just see if you get it. See that you get it working. Just the one thing. You don't have to write a MATLAB interface for just this, but it's fairly simple, and it'll tell you whether or not you're doing it right, because you should get the non-zero pattern of R as a binary matrix. You don't have to return this to MATLAB. You don't have to have the RX component. It's just all ones. In the C code, this would just be simply ignored. In the symbolic analysis. Of course, the numerical work will fill that matrix with values. So I've got here now the pseudocode. Okay, so you have R is all 0, except you know its pattern, row by row. Now, the other thing you need to know is you need to know A stored by So the way I like to think about this is you're not transposing the matrix, you're just converting it from compressed column form to compressed row form. Okay. Technically, it's been transposed. The other thing that you have to have is you have to have now, see, this code right here requires A in column form, but now you need A in row form. So again, just transpose it. And here you need both the values transposed as well. So now you've got A stored by row. So now you've got so now you have the pattern of R stored by row as output from the symbolic analysis, but with no numerical values. And you may wish to go through, it's probably most convenient to go through and set Rx to be all 0. So at the beginning of the numerical code. And now you've got the rows of A, one at a time. And so the algorithm here is you grab a row, you go through each row, and you first scatter it into a workspace. So this is a compressed sparse row, and you scatter that. Let me actually draw it. Maybe you draw it here. You scatter that into a workspace. I called it A, little a. So it's a size n workspace, and to keep track of this non-zero pattern, you won't have to do, if you find yourself saying, oh, I've got to do set union operations, or I've got to figure out what the pattern is, and you're doing the wrong thing. Okay. In the numerical analysis. And the symbolic analysis, as I said, should take you all of 10 minutes, 20 minutes, whatever. Because you're just taking the existing QR, ripping out the numerical values, not computing the V, getting yourself a new code that's just doing the pattern, just like the Cholesky code you did. Okay, you're just using those reach functions one at a time. It's not actually the eReach function, but it's similar. It's doing a similar behavior to find the non-zero pattern of R. So the hard part of this project is not the symbolic analysis. You can almost pretend this is already done. It's so simple. So this is not where the real bulk of the work is, although you have to do this to get your code to work. So try that first. And then actually the next thing to do after that, I would recommend, is this is pseudocode. This is not real code, but turn this into working MATLAB code and ignore sparsity, except for the parent array. Okay, you can find that in MATLAB if you wish. And get this code to work in MATLAB. So then you know what you're doing numerically. You know how to compute the Givens rotation. You know how to do a Givens rotation between the row of A and the row of R. Okay. The Givens rotation is explained in the book. It's just a very simple, 4-line piece of code that computes the coefficients. I saw one student was trying to actually construct I think it's sparse matrix, a 2x2 sparse matrix, and a 2 by n sparse matrix, extracting out the rows, build a matrix, and then do the matrix multiply, calling the CS multiply function. No, don't do that, because the multiply function takes time proportional to the number of columns in the second matrix. That's n. So that you've got an order n loop inside of order n loop, and that is, in other words, outermost loop, you're going through each of the rows of A, which if there are m of them, and if for each one of those you spend order n work, then you have an n squared algorithm, n times m. That is not a sparse algorithm, obviously. So that is completely verboten. That's forbidden in German. But see, I'm more than half German, so I can say that. But in terms of linear algebra, this is what you're computing. So this is what you would do in MATLAB, right? But not in the C code. And so what's happening here is there's two things to do here inside this. There's an if test here, and let's ignore this piece right here. In fact, you could ignore that, and the code would still work. It would just be a little bit slower. Okay, if you left this out, and the code would still work. In fact, you might want to write the MATLAB code just to see that in fact works. So this piece right here, do a Givens rotation between these two rows. I didn't give the details of that because that's something, I'll give you this discussion right here. And the key observation here is that you're doing a Givens rotation between two things. Between the kth row of R and this workspace A. This is scattered, this is in full form, and this is sparse. I should also add, by the way, when you scatter this into the workspace, there should be a loop invariant in your code implicitly that says initially A is all 0. Don't go through and set A to be 0 inside the loop, right? That's ridiculous. Set it all to 0 outside the loop, and then use a loop invariant that says it's all 0 here, and at the end of this each row of I loop, it will be reset to 0 because you've cleared just the pieces you're working on. Okay, don't have an order n loop inside of order n loop. All right, so to do this scatter operation, to do this rotation, we've got to rotate, do a Givens rotation between two rows. One is stored, so you can think of it this way, but one is stored in a sparse form, one is stored in a full form. Right, this is the row of R, and you have the non-zero pattern of the row of R already computed. You see, these Givens rotations that you're doing, they aren't going to give you any surprises. It will not be the case that you will come across, suppose that your pattern of R says that, okay, run the fifth row, and there's that entry, and then here's 11 and 42, 42 being my favorite number. Right, so there we have the non-zero pattern of the fifth row of R, and we want to use this to annihilate the A matrix. In particular, we're annihilating A of 5. Okay. It will not be the case that, say, for example, the 12th entry of A will be non-zero. It cannot be. Because when you do this Givens rotation, on the output, these two rows become the non-zero pattern of the set union of both of them. So if this is non-zero in the row A before you start, then this will be non-zero here when you're done. But wait a minute. You've pre-computed the pattern of R, so that cannot be there. It wasn't there, so it's not here. You don't have to check this to see is that 0 or not. You know it's got to be 0. This is the non-zero pattern that defines all the positions you need to rotate with. So you go through the R vector, which is compressed, and you say, oh, here's R, row 5, column 11. Do the Givens rotation between, do this little 2 by 2 multiply, which is these coefficients, what's it, C, S, minus S, and C, or something like that, times these two values. These two values, you don't make a 2 by 1 matrix to do this, but call this R11 and A11, if you will. These two values are going to change. R11 prime, A11 prime. They're going to change, and A11 is just A11. And you get 11 from the RI list. You know what column, to work on from RI. Although if it were me, I would write it this way. I would have a line in my code that said this in his initialization, because I would use this to remind myself that, hey, yes, I've got the compressed sparse matrix version of R, but it's stored by row. So this is really a list of column indices, RJ, not I wouldn't call this RI in my code. But anyway, that's what I would do just to remind myself, because I get rows and columns mixed up all the time. So this is what I mean here in this problem statement discussion here, where I say, look, you don't need to keep track of the pattern. If you find yourself doing set unions or making lists of integers and such, you're along the wrong path. Okay, you're not doing the right thing because you have the pattern already. It's a subset of the kth row of R. And so the goal of the Givens rotation then is to annihilate, when you're working on the fifth row of R, the goal of the Givens rotation is to annihilate this fifth entry right there. Set it to 0. So you'll be finding the Givens coefficient, which is, it's discussed in the book. If you have two entries of a 2 by 1 vector, A and B, you can find these coefficients that sets the second one to 0. That's and it's 4 lines of code in the book. Just use that to find these coefficients. But when you're doing this right here, don't write this as a 2 by 2 matrix multiply. Just write this out. Write this as R new equals, C times R11, plus C times R plus S times A. It's 2 lines of C code to do this matrix multiply, right? Just work it out algebraically. Now, one caveat here, okay, when you've got to assert, and I would add in a loop, an order in loop inside an order in loop, but only for debugging. That at the end of the day here, at the end of this for each row I of A loop, inside, just at the inside of this loop, so every iteration of this outermost loop, you should just check, or at the top here, you should just assert that all of A is equal to 0. Just check that. Don't turn that in that way. Comment the code out. Okay, but check that. And if you find that you failed, there's two ways that can happen. First of all, this is an algebraic 0. Okay? If you go through and apply all these Givens rotations, you do need to apply the Givens rotations to this first entry in column 5 to zero this out. This will become algebraically 0. Okay, and this will become something else, what it ought to be. But because of floating point round off, this will not be 0. This will be, 10 to the minus 16. All right. So if it's the very first Givens rotation, say do the computation if you wish. Just maybe call a little function that does this piece of work. But when you're done, and if it's the first one you're doing for position K, using the same letter K that I have defined there, you'll get some sort of epsilon here. Well, just set it to 0, force it to 0. I do that in one of the MATLAB codes in the book. The thing that I know that's being set to 0 will be 0. And because you're walking up, you're basically going through one at a time and annihilating one entry out of A at a time. And then you walk up to the parent. You see, that's going to zero A out, because that'll zero out this position. And what you'll have left with is other non-zeros. But those non-zeros will be a subset of 11, 42, and 44. Actually, you'll have all of those by now. Okay, because you've done the rotation. Some of these actually may be 0 numerically already, because R starts out all 0. So this entry here, for example, could be 0. Okay, it could start out 0, and this could start out 0, so it's still 0. But symbolically treated it as if it is there. There are some optimizations that you could use to exploit that fact, but we're not doing that in this project. That would require more dynamic computation that I'm not requiring you to do. I'm trying to keep this simple, if you can believe it. But what's going to happen is you're going to go to the parent. Well, the parent of 5 will be the first off-diagonal non-zero, which is 11. So that gives you the very next thing to annihilate. Position 11. So you see this, every row of R, all right, is a subset of its path to the root. And you're walking the path to the root. So you're going to see every non-zero in the A vector. And you will annihilate each one at a time. So by the end of the day here, the bottom of this loop, or at the top of here, the vector A should be all 0 numerically, without having to worry about going back and setting it to 0. You will have made it 0. That's the whole purpose. If, in fact, you also truly annihilate this entry, because if it just goes to epsilon, it's close to 0, but it's not quite. It should be 0. This is where we want numerical cancellation to occur. It actually is supposed to cancel to 0, but it might not. Okay, so force it to 0. And if you do that, then A will be all 0 at the top of the loop, without you going through a loop. A1, 0, A2 set to 0, A3 set that to 0. I mean, that's ridiculous. That's not a sparse code. This other thing right here, this test right here, if row K is 0, then slap in this vector A into R. That does just a gather, right? because this is a full vector, that's a sparse vector, and then break out of the while loop. We're done. We can terminate early. And the idea there is if this vector here is all 0, and you're doing an annihilation with the A and this row of R, the kth row of R, well, then how we want to annihilate this to 0. Of course, the goal is then to go to the parent and annihilate that to 0, and then go to the parent and go to the parent, and do Givens rotations to annihilate all these to 0. But there's a lot cheaper way to annihilate all these to 0, and that is to swap these entire rows. Just swap this row with that row. And a swap is a special case of a Givens rotation. In fact, if you did this, if you computed the Givens coefficient for this matrix, if you wanted to compute the Givens rotation, okay, which is a little 2 by 2 orthogonal matrix that annihilates the second entry to 0. Well, if the first entry is already 0, then what's going to happen is the orthogonal operation does not change the 2 norm of a vector. We learned that earlier. And it annihilates this thing to 0, so this has to be b. Well, it might be absolute value of b, actually. But negative b is fine. Negative value is fine as well. So we could just make this b. Well, there's a name for this. This is a swap, and it would be 0, 1, 1, 0. Algebraically, okay. And if you were to try to do the Givens rotation, you would find it's numerically 0, 1, 1, and 0. All right. It's just a swap anyway. So this Givens rotation, if you try to do it, would just tell you you're just doing a swap anyway. Okay, don't compute the Givens rotation to decide, oh, I'm going to do a swap. Okay, decide you're going to do the swap and swap. And when you do the swap, it's a special case because all of these entries now are all 0. And now this row R is filled with stuff. So this is just this statement right here. That's the swap, if you will. And you're done. Now, little a is all 0. You don't need to put all zeros in there because, well, you do actually. You need to make sure that all these entries, when you put them here, actually you need to set all these entries to 0. But don't go through k through n. That's ridiculous. Again, don't go through, for column j equals k to n, set this to 0. That's not a sparse code. You know the pattern of the little a vector. It's the pattern of the kth row of R. And so iterate across those columns. That will clear it. That will do it. The other question is, how do you implement this test? You should be able to implement this test in constant time. I don't know if I mentioned that here. Do I mention that? This test can be done in constant time. And really the simplest way to do it is based on the following observation. Once a row has any non-zeros in it, then you're not annihilating any entries in R. So once a row has non-zero values in it, a row of R, it will stay that way. So this slap operation, taking this and slapping it into here, only occurs one time for every row of R. So you could just have a flag here that says that starts out as all 0 for whatever. Have a vector here of size equal to the number of rows of R. Okay. And then 0 says the row of R is all 0. And the moment you do this operation, you set the flag of k to 1 to say, oh, now it's got something there. So it's this very simple flag. Now you have to ask the question, well, what's the most efficient way of implementing a flag vector? Well, you could just allocate an array of integers and just set them to 0 and then flag them by setting them to 1, and that would be fine. Okay. You could actually implement this without that extra workspace, though, because all we require is a flag vector, one bit of information for every row. And we have lots of workspaces already that are of size equal to the number of rows of R, which is n. for example, you could use the CS flip macro on the column pointers, or the column, not row pointers, RP, for instance. And they could start out, the simplest way to do that would be to start out flipping use CS, the flip macro, to mark every row of R as empty. So you flip, and once it's flipped, you don't really need to look at the pattern because you know it's all numerically all 0. And then when you do this thing where you slap in this, the test would be to ask, is it flipped? And then when you assign this row vector A into the matrix R, you unflip it. And when you unflip it, now the column pointer becomes usable because now it's in the positive values from 0 to the number of non-zeros. That would be what I would do. It adds a little bit of complexity to the code, not a whole lot, but it rips away an order and workspace, which is always a good thing. But if you want to do this binary workspace vector and just set the flag 0 and 1, that's fine too, because this will not destroy your asymptotic time complexity or your memory complexity, because you're not going through this flag vector looking at all of it every iteration. That would be n-squared work, obviously, and that we don't want to do. You won't be doing that. So that would be fine either way you want to do it.
Could you not also check the numerical value?
That's a good question. Yes. Could you not also check the numerical value? Okay. That's dangerous.
Yeah.
Okay, and here's why. That's a very good question. And somebody asked me that question before, or I was talking about this before with another student. That's dangerous. The reason that's dangerous is because suppose you're at the kth step of factorization. Okay, first of all, you're in MATLAB. You're calling your code only from MATLAB. So you know your A matrix on input, okay, has no non-zero values. However, if you were not in MATLAB, then this A matrix here could have explicit zeros in it. Okay, that's one concern. Well, let's ignore that because let's suppose we're only in MATLAB. Okay, so that problem goes away, but still the problem stays. Because what can happen here is, let's suppose you do a Givensrotation on the leftmost, which is this one, and it sets this to 0. All right. Well, it's quite possible in that in the process that this gets set to 0 as well. Or maybe it's, let's see, or maybe this, yeah, because maybe this entry so we annihilated this to 0. Maybe when we did that, this also happened to cancel out to 0. So we've just introduced a numerical entry which we are accounting for in our symbolic computation, but it is numerically 0. Okay. So in other words, A did not start out with hard zeros, with explicit zeros in its pattern, but now it's got them. Oops. Okay, now look what happens. Now consider the case that little a, the vector, could have a 0 here. Okay, you look at this and you say, oh, look, that's 0. I can copy this in. And you do that. So you copy the 0 in here, but it stays 0. So far, nothing's broken. That works just fine. What happens the next time? The next time this happens, you look at this and you say, oh, look, that's 0. Oh, I can copy in. And you just obliterated these values which are there. Very subtle bug, which you would introduce, which may not happen in every matrix. In fact, it would be uncommon. This would work on 99 out of 100 matrices. In fact, it might work out of 999 out of 1,000. It might not be triggered by your tests at all. Okay? But the moment you deploy this in a real commercial code, you stick it in MATLAB or something, and you ship it to your customers, 1 week later, someone comes back and says, hey, there's a seg fault here in \, and MATLAB crashes. Oops. So you have to be paranoid about those sorts of things. When you're writing software, it pays to be paranoid. Anyway, so those are some of the things you've got to look at when you're playing with this QR. It is due Friday. I want you to start working on it this week. I may decide that project 6.5 is just more time for this one, okay? But I haven't decided that yet. So assume that the project is still due Friday. Okay. I may decide to have a different project for project 7. I want a report for this one too at the bottom here. Write a short report with some tables or plots. Just, a page or two. It doesn't have to be much. Okay, just tell me, look, it's just as fast as the MATLAB sparse QR until the matrices get so big, and then it's a little bit slower. Okay, if you find for very, very large matrices that you're a million times slower, okay, then you've done it wrong. Right? That's a big indicator that you've got an order and loop inside of order and loop. You've got something broken asymptotically, and believe me, I've seen such codes submitted, and it's very depressing to be teaching a course on sparse matrix algorithms and to see an order and loop inside an order and loop when that kind of kills the whole purpose. What are we doing in here? We might as well just do a dense matrix computation and forget the whole course. So that's rather pointless. So don't do that. For debugging, for developing, that's fine. But if you're stuck, and if you're stuck somewhere, fine. But not in the final analysis. Okay, so that's, and as I said, I think this is probably the hardest project yet. I've given you some pointers to use for it to work, but I haven't given you lots of details because by now you should be able to figure out the details. The other thing I would again recommend is you take this pseudocode here and turn it into real MATLAB code. It won't be much longer than this. It'll be about the same length. A few extra lines of code here. And that will tell you that, okay, if you get that to work, that will tell you that you understand the numerics of the code. The parent you'll want to get from there is the function Etree in MATLAB. You want to find the Etree of A transpose A. I think I actually have a code in here that does that. The elimination of the matrix A transpose A, it's the Etree function called with the call, quote unquote, parameter. Yeah, I do that here on page 80 of the book. I already have that. So this code right here and the code on page 80 are very similar to each other. This code in page 80, though, is not suitable at all for a sparse implementation because it puts the data back into the A matrix. Okay, but we can't do that. We don't. In the sparse case, that's very awkward to do. We're putting the data into R. See, at the end of the day, A becomes R. Okay, we're not doing that. All right, so that's why this code right here is not, the code in the book on page 80 is not an outline of what you're doing. The outline of what you're doing is right there, but they're similar enough that you should be able to implement this in MATLAB to get it to work. It will be slow, okay, but that's okay. Don't even use sparse matrices except for the parent thing. Just blunt instrument dense matrix operations just to tell yourself that you understand the numerics. Okay, so that's QR. Any other questions about the project? I've probably given you more than you asked for.
Can we optimize the Givensrotation step if the diagonal of A is already 0?
Can you optimize the Givensrotation if the diagonal of A is already 0? Well, there's really no diagonal here. You mean the kth entry?
The kth entry, yeah.
Oh, yeah, you could, definitely. You could skip it.
Okay.
That's optimizing it. You just skip it altogether. Yes. And a real commercial quality code would do that. Your code, if you didn't do that, your code would still be asymptotically correct, just a little bit slower. But yeah, there's lots of cases like that. If you think about them and realize, hey, I can do this better. And that's one of them. It's a very good observation. Yes. This is exploiting the special case in the other direction, where R starts out to be 0 and A is non-zero. Just slap. Well, the other thing works too. If the thing you're trying to zero is already 0, well, skip it. Don't do it at all. In fact, if you compute it, can you imagine what's going to happen here? If I find a Gibbons rotation, okay, the Gibbons rotation is an orthogonal matrix, so it's not going to change the 2 norm. And it's going to zero this out. So what is this value here? It's got to be A. It could be plus or minus A, actually. It could change the sign. And so, in other words, this Gibbons matrix must be identity, or say negative identity, which basically says skip it. And certainly identity works fine. Okay, so you're operating, there's no work to do here, right? You can skip it. It's the cheapest Gibbons rotation on the planet. Is none at all. Yeah. There's lots of things. The other optimization which would reduce the time complexity, but not by an amount that's easily formulated. But I'm not asking you to do this. Is the following observation. The observation here is that this pattern of R is the final pattern of R. Okay. But it's not the current pattern of R. Imagine if you could keep track of the actual non-zero pattern of R at the current moment, dynamically. In the final analysis, you know what the pattern will be. So you know the length of every row, for example. Okay, so you know the length of every row. You could keep track of the pattern of each row of R as you are operating on it. At the end of the day, you know the final outcome. But then what that means is that as you are working on it, these Gibbons rotations are shorter because the R starts out as empty. And you put one row of R there, one row of A. You slap it in. Well, what if that's 5 non-zeros? And the final row of R will be 100. So what that means is what you're doing every time you're operating on this row of R, you're doing 100. You're working on 100 entries of this matrix, of this vector A, every time. Well, that'll be how big it'll be at the very end, on the very last time you touch this. But it's growing there. So as it's growing, you could do this, do 5, and next time do 12, and then do however many non-zeros you actually have at the current moment. So it's growing dynamically, and then it stops. That's a much harder algorithm to implement, though. Okay, then you would have to keep track of the pattern of R you have so far. Okay, that would change the statement. You would need to keep track of the pattern. At the very end of the day, you know what pattern you will have. It's a bound. You have this nice clean bound. You know where you're going, but you don't know where you'll be in the middle. And then, furthermore, you could further optimize this then by saying, well, what order do I want to annihilate the rows of the matrix? Okay. What if you had the following scenario? Suppose you have a dense row of A. Suppose A1 is completely non-zero. R then will be a completely dense upper triangular matrix. All non-zero. So where's the sparsity? Well, what you can do is don't do this row first. Do all the other rows first. So these are all very sparse. So R is nowhere near its full density. It's just got a little bit of non-zeros in it. Okay? And then the very last row would be this one. So you take this and you annihilate this entry. You do a Gibbons rotation. Well, in the process, every entry in R becomes non-zero. and you annihilate that. And then you go to the parent, which is the second column. And so R just suddenly explodes in size. But it explodes late. The final outcome is still the same. R has n squared over 2 non-zeros. Okay. But, so why bother to exploit sparsity? Well, you can exploit sparsity along the way. Okay, in other words, you do a sparse QR of everything, and then the very last step, R becomes dense. And the very last step, this work right here, will be order n squared. Because it's a dense row, and you're annihilating you're touching every entry in the R matrix. So it's n squared over 2 times the Givensrotation, flop count, whatever that is, 3 or 4, 6 operations, whatever. It's n squared. Just for this one dense row of A causes n squared work to annihilate it. But you do that last. Now, what happens if you do it first? Then R starts out all non-zero. And then you want to do Givensrotation to annihilate these two. Well, when you do this, you annihilate this, and you set all this to non-zero. And then you've got all this work to annihilate it. All right. So you are doing all this work, but a more concise code would not have to do that. Because you're just walking up the parent. But in fact, if these are already 0, you can skip all that work. So, and you don't even have to look at those symbolically. So this algorithm is a whole lot more subtle than it initially looks. You are just implementing it you're implementing an algorithm which is the base level asymptotically correct algorithm. Okay. All right. So now I've got 7 minutes. So let me leave QR behind and let me go on to reciting Robert Burns' poetry. No, I'm not going to do that. I'm tempted, right? I promised my brother I would not embarrass his son, my nephew, so I'm not going to do that. Okay, ordering methods. And I want to jump into this, and I want to leave chapter 6 behind. So this is an NP-hard problem. So we can't find the solution. There's several strategies for heuristics, but the goal here is to take a graph, find an ordering to reduce the fill-in. And minimum degree is the easiest way to do this. Okay. And let me show you a picture of this because I only have 6 minutes. I'll walk across the algorithm. But here's the idea. You've got a matrix here, and you want to order the nodes so that the number of non-zeros that are introduced into the graph or into the matrix equivalently is minimized. Now here I'm assuming I already know the order from 1 to 10 that I'm going to annihilate. So I'm going to first annihilate node 1. So what happens when you do Gaussian elimination on node 1? Well, you take this equation. This is an equation in your matrix. And you're going to use it to zero out these first 2 entries. In the process, you're going to take this row and add it to here and to here. And that makes these entries, where are they? Here, now, non-zero. So think about what happens in the graph. If this is a node in the graph, node 1, it has edges to nodes 4 and 6. 1 has edges to 4 and 6. So this is the graph of this matrix here. And I just put the nodes in some arbitrary position, of course. This matrix doesn't have any positions of the rows and columns. This graph does. And graph elimination corresponds to Gaussian elimination. You take this node, you annihilate it, but in doing so, you add an edge to all its neighbors. I like to use a story here to explain what's happening to this graph. You have a group of friends at the university, and you want me to use the morbid one or the more friendlier one?
Morbid.
Morbid? Okay, morbid one. You've got a group of people who know each other. These are the relationships between them. So 3 and 6 know each other. Okay. And the goal is to kill everyone in this graph. I told you you'd use the morbid one. Morbid one. So I'm going to kill node 1. Okay, it's dead. In the process, his friends go to his funeral. So his friends 4 and 6, they, oh, hi. Yeah, it's so sad. One is dead. Oh. But at the funeral, they get to know each other. So now they know each other. So every attendee of the funeral now knows one another. The goal of the killer is to eliminate everybody. Everybody's going to get killed. But in the process, minimize the number of relationships, the friendships that people have. You want to kill the outliers first. Kill the loners, right? You want to minimize the number of non-zeros introduced into this graph, which is the number of relationships. So this is not a good thing here, this relationship. You want to kill the people in order that minimizes the number of, the total sum attendance of all the funerals. Okay? Imagine you have a list of people who go to the funeral 1. Well, it's persons 4 and 6. When you annihilate 2, 5, 6, and 9 attend the funeral, but now see they're pairwise connected in a clique. Okay, so every time you annihilate someone, you have a list of people who go to their funeral. And now you want to ask the question, well, who do you know? Who do you know, say, number 6? I'm not a number, I'm a free man. Okay. Number 6 says, well, I know 5, 9, and 4. I know and 3. I know 3 originally, because I knew 3 from the beginning. But I know 4 because I went to funeral 1. And I know 5 and 9 because I went to funeral for person number 2. So now, if you'd like to represent this data structure most compactly, okay, who do you know? The non-morbid solution, the non-morbid analogy to this, by the way, is these are people at the university and they graduate and they hold a party, oh, one graduated. Let's have a party. So which parties have you been to tells you who you know. You know some people originally, and then you know people according to how many parties you've been to, graduation parties. All right. So how would you represent this graph? You could represent the graph by saying, well, person A, person K, who do you know? Well, here's the 100 people I know. All right. So you have a list of 100 people. But now, wait a minute. This person K knew 5 people originally, and he's been to 7 graduation parties. So, but wait, that graduation party, that's like posted on someone's Facebook page. Everyone who's ever gone to that party, they're already in the list. So if I wanted to find out, I have a concise representation of the adjacency of K. Who is K connected to? I could say, look, K knows these 5 people originally, and he's been to these 7 parties. And then I could go up on the wall here, and where I have a list of all the graduation parties, or all the funerals, whatever. And every list just tells me who has attended that party. And I could just take the set union of all that to find the 100 people. Because the other person over here, and so what I've done is I've reduced this list from 100 down to 12. And that's really powerful, because when that happens, the number of integers required to represent this new graph, this is now called the quotient graph here, is proportional to the number of non-zeros in the original matrix. It's actually not just proportional, it's limited, strictly limited by the number of edges in the original graph. In other words, this algorithm can operate in place. This algorithm cannot, because we're adding these new edges. These new edges we're adding correspond to the number of edges in the factors of this matrix, which could be enormous. But here with the quotient graph, we reduce that to working in place. So this takes space proportional to the number of non-zeros in L, which is huge, A, which is small. So here, we don't actually annihilate node 1. We just replace it with a representation that says, this is the graduation list for node 1. These are 4 and 6 are the people who attended 1's party. And when I annihilate 2, I don't remove 2 from the graph. I just replace it with a new node that says, this node 2 says to me in the graph that nodes 5, 6, and 9 are now all pairwise connected in a clique. So now if I ask node 6, well, who do you know? Here I know 4, 3, 5, and 9. But I ask node 6 here, well, who do you know? Well, I know 3 originally. And, well, I know 5 and 9 because I met them at the party for 2, or the funeral for 2. And I know 4 because I met him. And that gives the same answer. Then furthermore, what can happen is that these party lists or funeral lists can be absorbed into one another. Okay. What if you have and I'll finish really quick here. What if, for example, at this point you annihilated node 6? If you annihilated node 6, you form a clique of its neighbors, then these cliques are a subset of the new clique. Or party 1, 2, and 3, the attendance list for those 3 parties would be subsumed inside the party of list 6. And anyone who attended party 1 will also go to party 6. And we'll have that list in their adjacency as well. So what do you need to list for party 1 anymore? It's of historical interest only. We can throw it away, and we still have the ability then to find the, say, adjacency of node 5. Node 5 went to parties 2 and 3, but once 6 becomes annihilated, it doesn't matter. Node 5 is in the 6th party, and that tells you the adjacency for 5. So that's the quotient graph, and this is what's called element absorption. We can annihilate, you can remove these nodes after later. Another way of looking at this, if you've got a posting on the wall of all the funerals, and who's been to what funeral, this is the morbid tale. The moment you kill someone who's been to a funeral, you can remove that list that they're in. You don't need it anymore, because their funeral will have all those people, because they all got to know each other. The new funeral of that newly dead person, I told you this was morbid, will have in its attendance list all those people on that list in the new list. So you can throw away the old list. Or the graduation party, however you like to think about it. Okay, whether you're bloodthirsty or not. Anyway, so that's the minimum degree algorithm. And I'll go into a lot more gory details. Ooh, that was not supposed to be a morbid mention. I'll go into the gory details on Wednesday. Thank you.